there. Welcome to Astraveo's continuing education series, where for our podcast listeners, we talk about mathematics, the physical sciences, of course the natural world, and our personal favourites, astronomy. Now, you know Joseph and I are all up in and about astronomy. We get super excited about that stuff. So let's get going. Welcome to Astraveo's continuing education series, where this evening we will be talking about Newton's laws of motion. Now, these were derived by Sir Isaac Newton nearly 350 years ago in Great Britain. Now, Sir Isaac Newton is a very famous character in history. He was a great philosopher, a great writer, a great scientist. He worked at the Royal Mint. He was the treasurer for the king, essentially, in terms of counting and printing money. He's also famous for having discovered the fact that light travels in straight lines. But today we're going to talk about his discovery of his laws of motion, which he derived by observing the world around him. Now, I've already written the first one out on the board here because it's a bit of a complicated one in terms of words. And what it states is that any object, a body, a rock, an apple, a tree, a car, anything, remains at rest, that means it's not moving, or that it continues its motion in a straight line unless it's acted upon by an external force. Now, that's a lot of words to describe something quite simple, actually. If it's at rest, that means it's not moving. Its velocity equals 0 meters per second. Don't forget, it's a vector. So in here, we're going to write in any direction. A vector has to have a direction. In any direction. Unless you apply an external force. Now, for instance, this Sharpie pen sitting on my hand here, it's not moving. It's at rest. Its velocity is 0. Now, to make it move, I have to apply an external force. I have to wiggle my hand, I could move my hand, and the force of gravity would make it fall toward the Earth in the Earth's gravitational potential. Or I'd have to do something to it. I could jump up and down, for instance. So, unless I apply an external force, it will remain at rest sitting on my hand. Now, the same is true that if this was in motion, in a straight line, it would continue to do that unless we apply another external force. Now, here on the Earth, for instance, if I were to throw it through the air or let it roll across the ground, there is an external force being applied. It's either wind resistance or it's resistance friction, really, with the Earth or the ground. So that will cause it to either change direction or actually slow it down. It will reduce its velocity. Now, we have a good example of that. If you've ever thrown a rock or an ice hockey puck, say, on a frozen river or a frozen lake, that object will go very, very far without too much effort. That is because it has very, very low resistance on the ice, and therefore it will keep going in a straight line unless you apply a force. So if the wind were to blow very strongly and make it change direction, that would be changing its state of motion. It's changing its direction. In space, for instance, where there's no wind resistance, there's no friction with anything, if you were very far away from any stars or any other galaxy or any planets, and you had an object moving, let's say a piece of rock, and for whatever reason it was moving, it would continue moving through space in a straight line, uniform motion, neither accelerating nor decelerating, unless we acted upon it with a force. Now, that could be due to gravity of a nearby galaxy, or if it came near a star, for instance, or if light was shining upon it from a star, that could impart a momentum, so that could change its velocity. But otherwise, if there's nothing to stop it moving in a straight line at constant velocity, no external force, it will keep doing that forever. And that's what Newton's first law says. So really, it's a statement of how objects move unless you apply a force to them. They will either stay stationary at rest, that's what stationary at rest means, it's not moving, or they will continue their motion in a straight line unless you act upon them with a force. Okay, so that's Newton's first law. Okay. Now, Newton's second law is actually a little bit easier to understand, perhaps, because it has an equation. Now, I know some people here are thinking, oh gosh, we don't like equations. Well, at Astraveo here, we're scientists. Joseph and I are scientists. We love mathematics, we love equations, we love science. But equations aren't necessarily complicated. The one I'm about to show you is actually quite easy. Now, Newton's second law, let's see, no squeaky pen syndrome at the moment. Newton's second law states that any force any force, whoops, there it is, that you apply, squeaky pen's coming back, to an object results in an acceleration directly proportional to the force applied, acting in the same direction. Now again, that sounds complicated, but when we break it down, it actually isn't too bad. Okay, so let's just check that we've got that right. Any force that you apply to an object results in an acceleration directly proportional to the force applied, acting in the same direction. Now it has a very simple equation associated with it. Any force, F, it depends on the mass of the object times the acceleration. Acceleration. And that's it, really. Now, here it says, any force that you apply to an object, whoops, I forgot the an, I apologize, to an object, results in an acceleration directly proportional. Now, that's a strange mathematical way of saying, however big the force is, the acceleration is going to be just as big. Directly proportional means relies upon. So if you increase the force by a factor of 10, the acceleration goes up by a factor of 10. You reduce the force by a factor of 3, the acceleration is reduced by a factor of 3. Now, there's this special bit at the bottom here, acting in the same direction. So if you, these are vectors, so I'm going to do a special form here. I'm going to put this vector symbol with an arrow. So if I apply a force to an object this way, it's going to accelerate in that same direction. So I'm going to put my vector arrow that way as well. Now, one thing we haven't seen, it's not really listed in the description of the second law, is the mass. The mass of the object matters a lot, because the more massive the object is, for a given force, the less acceleration there is going to be. Now, that makes sense when you think about it. If I were to push this pen here on my hand, let me put my other pens down. If I was to push this pen here in my hand really quite softly, it will move, obviously, because this doesn't weigh very much, its mass is not so great, and I can make it roll across my hand. Now this, if there was an African elephant sitting on my hand, if I were strong enough to hold the elephant in my hand, if I pushed it with the same force, could I accelerate the elephant as much? And the answer is no, of course, I definitely could not. And so the mass really matters. Now, another way of thinking about it is, let's say that you're driving a car, right? Or your car's and it's in the middle of winter. Your car stalls out and your car won't move, but you've got to get it off the road. If it's a small car, as you might see in Europe, for instance, a little Mini or a little Fiat Cinquecento, if you were to push that car to get it off the road because it's blocking the road in the ice and the snow, one, possibly two people might be able to push that car fairly easily because the mass is not so great. But if, for instance, you had a dump truck which was capable of holding, say, 20 tons, maybe nearly 45,000 pounds worth of rocks or sand or grit or whatever the heck it's transporting, could one or two people push that truck out of the road? No, they definitely could not. The mass is so much greater than a small car, it would be very, very hard to push. Now, eventually you might be able to make it move, but it would move very, very slowly compared to how fast you could make a small car move. So mass really, really matters. Okay, so like all good astronomers, let's make some space and get rid of our writing here for the second law. Okay, so F equals ma. The force is proportional, directly proportional to the mass and directly proportional to the acceleration. So it's often written, I should have written, given I used words here, this is force. It's often written F equals m for mass dot a times acceleration. F equals ma. Now the units here, remember we've done dimensions before, are kilograms for mass. Acceleration is meters per second squared. So the fundamental units for force are kilograms meters per second squared. But astronomers have a special name for that, and in honor of Sir Isaac Newton, it's called newtons. So 1 Newton is 1 kilogram per meter per second squared. Okay, so that's very important. We do this dimensional analysis to make sure we get the units right. So F equals ma is a very, very famous expression in mathematics and science, and we use it a lot in science, in agriculture, in avionics, in the aerospace industry, in sports, in all kinds of ways we use it. Okay, so as you know, you've seen some of my videos already. I really like giving practical examples because when they're abstract like this, they're really difficult to understand sometimes. So the type of thing we're learning here, Newton's third laws, one might expect, say, a student who is 12, maybe 13 to start learning in school. So that would be I'm trying to do it relative to my children. Here in the US, it would be grade 8, possibly, grade 7, grade 8. In Europe, it would be year 7, maybe year 8, depending on which education system you're in. So let's have a practical example. Here is a surface. Could be a table, could be the earth, it could be a stone somewhere. I'm going to give it a block. Doesn't really matter what the block is made of, but it's going to be mass 5 kilograms. So automatically we have one of our numbers. M equals 5 kilograms. Now, if we have a person who is able to push this block with a certain force, we should be able to work out its acceleration. So I'm going to have a person push this block, and I'm going to assume that person is able to push this block with a force equal to, let's give it a nice sensible number here, 50 newtons. Now that's quite a big force, but that's okay. A 5 kilogram block is not so big. Now you'll notice there is a direction here. So we have satisfied our vector. A vector, don't forget, is a scalar quantity with a direction. So we're okay here. The force is a vector. 50 newtons from left to right on the whiteboard here. What we perhaps then want to know is, what is the acceleration of this block? What will be the resultant acceleration? Oops. So the acceleration will equal what? What do we need to know? Well, from our very simple equation over here, F equals ma, we have the mass, we have the force, so we can just rearrange our equation to get a, the acceleration. So let's do that. F equals ma. Now we want a, so we want m on this side, the mass on this side. And the way we can do it is let's divide by m and divide by m. Remember with an equation, when there's an equal sign, anything you do on the right-hand side of the equation, you have to do on the left hand as well, both sides. So m divided by m is just 1, and then you have f over m. So 1 times a is just a, and so we are left with a equals f divided by m. Whoops, squiggly m. Now we know the force is 50 newtons. We know the mass is 5 kilograms, so divided by 5. So 50 divided by 5 is 10. 10. And don't forget the units. It's an acceleration, meters per second squared. So there's our answer. Is that right? Is that really our answer? No. Well, good catch. We need a vector. We need a direction. So this is just a scalar. We need a direction. Now, if you remember when we wrote out the Newton's second law out on the board when we first started, we said the acceleration acts in the same direction as the force applied. So if the force is applied this way, the block is going to accelerate that way, in the same direction. Now we know that. That's kind of obvious. If you push something, the block or the object moves in the same direction you push it. If you were to lift it from the ground, for instance, push it this way, obviously the block would go up. So if we're pushing from left to right, the acceleration will be left to right, like that. So our vector will be that way, left to right. So for instance, if we need this block, for whatever reason, to accelerate with 10 meters per second squared, left to right, we know we have to apply a force, if it's a 5 kilogram block, F equals ma, 5 times 10 would give us 50. we would have to push on this block with 50 newtons left to right to make that block move left to right with 10 meters per second. So it can be very, very useful, especially in science and mathematics. So that's a really nice example. So what one might see on a standardized test, if they really wanted to test the student to see if they could figure out or if the student understood Newton's second law well enough, they might say something like this. For a mass of 10 kilograms, I'm sort of making this up, right? For a mass of 10 kilograms, starting at rest, how much force must be applied? Whoops, applied. Didn't write my P very nicely there. There we go, must be applied so that the block is moving at, I don't know, I could make some numbers up here, 60 meters per second squared. No, 60 meters per second, it's a velocity, after, let's make it easy here, shall we? 12 seconds. Okay, now this is a little bit more of a complicated question. It's not really when we're going to get into it. I'll explain it now, but on paper it looks complicated. So we have a mass of 10 kilograms. We have a block or a stone or whatever it is at 10 kilograms. It's starting at rest, so its initial velocity is 0. We know that. How much force do we have to apply to that block so that it ends up moving at 60 meters per second after 12 seconds? So we have quite a lot of information, but we don't have the information to satisfy F equals ma instantly. We need a force. There's F. We need the mass. Yes, we have the mass, but we don't have an acceleration. We have some velocities and some time. But an acceleration really is a rate of change of velocity. It's the difference in velocity per unit time. Now, we do have that information. So the very first thing we have to work out before we implement Newton's second law is work out an acceleration. So if you remember that acceleration, okay, I'm just going to call it acceler for this minute, is a change in velocity divided by the time that change is acting. Now it turns out we have a change in velocity. We have a velocity after 12 seconds, and we have a velocity after 0 seconds. It's at rest. Okay, so the acceleration is v final minus v initial, I'll call it for now, v initial, divided by the time. Now we have all those numbers, so we can work out the acceleration. We have a final velocity. We know the velocity after 12 seconds has to be 60 meters per second. The v initial was 0. It was at rest. And the time it took to do that velocity change is 12 seconds. So we are able to work out our acceleration. Let's do it over here. Now, I'm going to use A because, of course, A is directly going into F equals ma. So v final is 60 meters per second. V initial is 0, it's at rest, divided by 12 seconds. Now we have meters per second divided by seconds. We get meters per second squared, which is an acceleration. So 60 minus 0 is 60, divided by 12. My squeaky pens come back to say hello. We get 5 meters per second squared. Now, is that our answer? Not quite, because again, if you remember, this is a scalar. We need a direction. Now, we're going to have to assume a direction because we haven't been given a direction in the question. We can assume, I'm just going to say here, left to right. Left to right. So now it's a vector. So what force do we need? The question says, how much force must be applied so the block is moving at this speed at 12 seconds, having started from rest? Well, we now know the acceleration and we know the mass, so we should be able to work out the force really quite easily. So again, my famous astronomer move here, I'm going to make some space. It's kind of my thing when I do these podcasts, these educational series podcasts, so I think you're all used to this by now. So now I find, and this is just the way my mind works, but I think it really, really helps you understand the question, is draw yourself a little diagram. We have some surface. Didn't tell us what surface it was. We have a block, an object, and it weighed 10 kilograms. There's the block. We know left to right, if you remember, we defined the acceleration down here, left to right. The block ends up moving with an acceleration of 5 meters per second squared. There's the vector, left to right. That means the force must also be left to right, because that's one of the conditions of Newton's second law. The force is directly proportional to the acceleration of an object, and the acceleration is in the same direction as the force applied. So if the acceleration is left to right, the force is also left to right. So we need to know that force. So F equals ma, famous expression. The mass of the object is 10 kilograms. The acceleration we just worked out was 5 meters per second squared, left to right. 10 times 5 is 50. That's our answer, yes? You caught me out yet again. Well done. First of all, I forgot the units. There's newtons. And the vector, left to right. Left to right. Because don't forget, as we've defined earlier, F equals ma, but the acceleration has a vector, which means the force itself has to have a vector, because there's 2 vectors in the equation. And don't forget, these arrows define the direction. They're called vector bars. So we have answered the question quite completely, even though it was quite complex when it was written down. So we've turned a wordy question, which was perhaps difficult to understand, to pass in the beginning, but by some simple calculations as we went along and just understanding what the question was asking us, we've been able to apply Newton's second law, getting our units correct and getting our vector correct, because the force is a vector. So that's really nice. Okay, so yet again, let's give ourselves some space. Now, I did say Newton had 3 laws of motion. Let's go on to number 3. I really love number 3. It's one of my favorite things in all of science. Okay. And it's got a couple of different expressions, and they're really easy. So this is number 3. 1, 2, 3. It says, for every action, there is an equal but opposite, squeaky pen, come back, say hello again, reaction. So the way I was taught this, in sort of the shorthand version of this, for every action there is an equal but opposite reaction. We used to say when I was a kid, action and reaction are equal and opposite. What that means is the size of the action is identical to the reaction, but they're in opposite directions. There's a vector in there because there are forces. So this is action and reaction are equal and opposite. Now what that really means is we can see this in nature in all kinds of ways, actually. So for instance, if I had a basketball in my hand and I were to move my hand and let the basketball drop, what happens to the basketball? Well, of course, once it hits the Earth's surface or the floor, it's going to rebound back up. And the reason why that occurs is because when the ball hits the floor of the Earth, it imparts a force to the floor or the Earth. Well, the Earth or the floor imparts an equal but opposite reaction to the basketball, so it bounces back up. Now, it won't bounce back into my hand because there is some compression of the leather of the basketball. It makes a noise. There's a little bit of heat created when it hits the floor, and also there's air resistance. So the whole system is losing energy. Remember the interchange between kinetic energy and potential energy? that occurs. So even though the ball, in a perfect system with no air resistance, no energy loss due to noise or friction or compression of the ball would bounce back into my hand. But of course, that we can't ignore that here on Earth. So this is a really nice example. Another good example of Newton's third law you can think of as when we're flying in an aircraft, like jet airplane. So for instance, if you have the engine here, right? Well, I'm not going to draw the entire plane, mostly because I'm not a very good drawer, as I think you all know by now. Okay, so this is the jet engine. Oh my gosh, I'm not even sure I can draw the wing, but let's assume the wing's coming way out here. Okay, as I said, not the world's best drawer. So we're sitting in an aircraft up here. We're flying from Boston to Nashville to see some of my friends, maybe. Now, what's happening here is there's obviously fuel here. There's air coming in here. Now, once the air goes into the modern jet engine, it's compressed, it's mixed with jet fuel, and it is ignited. Well, at that point, the ignited exhaust is blown out the back here. So what happens is you are getting some mass of fuel. So the mass of the fuel is being accelerated out of the back of the engine. So you have a net force this way with F equals ma, Newton's second law. Well, if action and reaction are equal and opposite, what that must mean is the ignited fuel being exhausted out the back of the engine, it must push back on the engine with an equal but opposite force. So this force is going this way from the exhaust. That must mean it pushes back on the jet engine in this direction with exactly the same force. This force is the same as this force. Now, yes, the mass of the aircraft is much, much bigger. So this mass of the exhausted fuel is quite low, but the acceleration is enormously high. So when that jet fuel is being pushed out the back of the jet engine, because the jet and the plane with all the people on it and their luggage and all the goods it's carrying, all the cargo, and the mass is much, much greater, the acceleration forward is less. But that's why some of these big modern jet aircraft have 4 engines on them, because that means they can accelerate the plane much more, 4 times as efficiently. That is why these modern jet aircraft are able to fly, because the thrust that you get from the fuel as it's being expelled out the back of the aircraft, it gives an equal but opposite push to the plane going forward, because this is being pushed out toward the back, and makes the plane accelerate. It's able to overcome gravity, it gets lift from the wings, and it's able to fly. So we get a very, very nice demonstration of Newton's second law and Newton's third law, all in one nice example here. Modern aircraft, jet aircraft especially, are able to fly because of Newton's laws. Very nice demonstration there. Okay, thank you for watching.